Hello again. So I try to not generate any controversy. I try to keep the boring talk and not make any wild claims here. But I try to get a bit around this path of getting less ZooKeeper in Pulsar. So we started with a system that was like using ZooKeeper everywhere. It was a really spaghetti code in many ways, accessing ZooKeeper for multiple different reasons throughout the code base. And we kind of like, okay, to keep this. And we kind of like have this plan that we started a couple years ago to gradually move towards a place where ZooKeeper is not the only choice and probably not, at some point, not the default choice even. So I will spare the introductions at this point. And the first, before talking about Pulsar and ZooKeeper, I want to try to qualify what is metadata, because there are many misconceptions of what metadata is and what metadata means in the concept of Pulsar. If you look at the Pulsar cluster, this is like very familiar. So you have Pulsar consumers, and the cluster itself has composed by brokers, bookies, which store data, and ZooKeepers when using ZooKeeper. So the data path doesn't use ZooKeeper. So data path is really producer sending data to broker passing on to a couple of bookies, 2 or 3 bookies, depending on your configuration, and then back and on, and then to consumer. So there is no interaction in the data path with ZooKeeper. If you look at the metadata path instead, it is only between brokers will store some metadata in ZooKeeper, and bookies will store some different metadata in ZooKeeper. If you add in replication, it gets even more fun here. We have the concept of this global ZooKeeper, which is a configuration store. Essentially, it's just a way to have a single, strongly consistent view of your configuration when you're running with multiple clusters in a very dynamic environment. In this case, the configuration is stored in the global ZooKeeper, and each cluster will have their own ZooKeeper for the local metadata. So what is the metadata here? Let's first get some examples. So metadata typically is a pointer to data. So it doesn't contain the data itself. It contains information on where the data is located. And it is also used for things like service discovery. Which brokers are available, which bookies are available, and how can I, and at which address. Other example is distributed coordination, say electing a leader or figuring out who is the least loaded broker, for example. We've seen system configuration, like the policies and everything, and updating that dynamically, and provisioning configuration as well. If you look at the one most important examples here is the topics metadata. So we need to keep some track of some information per each topic. And since we use ledgers to store data, but we use for each topic and for each partition, we use a list of ledgers, because ledgers are, once they close, they're sealed, and we have to create a new one. So a ledger is a segment for us, and we have a list of segments. So we need to keep track of that. And that piece of metadata has to be stored somewhere. So this is called the managed ledger, which is a component that keeps a list of ledgers, plus some of the information, for example, where is the schema located? Or if we use compassion, where is the ledger that contains the compacted data? Another example is ledger itself. So ledger is a bookkeeper concept, and the bookkeeper uses ZooKeeper. And in this context, a ledger, essentially, this is kind of like, it is stored in protobuf, and it is compressed and so on. But if you write it down, it looks like this. So for each ledger, we need to know what is the ensemble size, what is the write quorum, the state of the ledger. If it is closed, we know what's the size of this ledger. We have some other information. The most important one is ensembles, which basically means it contains the list of bookies that contains data for this ledger. So we have 2 copies of this data. We know where to read it from. Bookie 1 and 2, or bookie 5 and 2 for the second fragment. So for service discovery, there are multiple examples. Finding the list of available bookies, which bookies are in read-only mode or read-write. Discover which broker owns a topic. A topic can be only served by one single broker at a given point in time. We need to find out. Or finding out what list of available brokers and the load of on each broker. Distributed coordination is kind of like a general problem in distributed systems, as in you have a cluster and you most likely want to do these kind of two operations. One is a lock. A lock can be used for acquiring ownership over some distributed resource, or it can be used for signaling that I'm doing these operations, so someone else shouldn't be doing that until I'm done, and maybe I will just be done with it, and you don't have to do anything. The other one is leader election. Leader election is kind of like, they're very similar in the implementation. Typically, the difference is that if you try to acquire a lock over something that is already taken, you will fail to do that. Leader election typically is that you try to become the leader, and if there is already a leader, just wait there in line until you be declared the leader. Once the current leader will crash and fail. And for system configuration, one simple example here is that we want to make sure that we can override the config files with dynamic settings that you can have per cluster, and override what each broker has in the config file. So and one example is the bookie rack mapping, so that we can update the rack awareness configuration dynamically. Finally, for provisioning, these are kind of like the policies. So we keep in ZooKeeper the metadata for tenants, namespaces, all the configuration for that namespace, authorization, all the ACLs. And typically, this is all highly cacheable metadata because it gets written very infrequently and gets read multiple times. So there's been like a lot of controversy about ZooKeeper. So what's the problem with ZooKeeper and why people want to get rid of it? First of all, I think that just to clarify what ZooKeeper is and what does it provide. So ZooKeeper is a consensus-based database. Means that you have a service in which each server is having the same copy of the data, and it can survive a number of, like say with five ZooKeepers, you can survive 2 nodes failures, which is good. One of the problems is that it is not horizontally scalable. So you can just add more nodes and have more throughput, more storage capacity, because each node has the entire data. And each node keeps the entire data in memory. So it is not very GC friendly because it keeps a big Java structure in the heap, and once that things grows, it's not very friendly on JVM. Also, another issue with it is that it takes periodic snapshot of the entire dataset. So if you have, like, say, a 5 gigabyte state in ZooKeeper, every few minutes we'd have to dump the entire 5 gigabytes on disk and then keep on rolling. So ZooKeeper was designed for some use case. I think we can stretch it up to a point, but it only gets up to a point. So comfortably, the maximum amount of metadata is really around like few gigabytes, up to 5 gigabytes. After that, it really becomes very challenging for ZooKeeper to handle the dataset. The other part is that running ZooKeeper with this kind of like a big dataset is really not trivial. It requires the right hardware, the right configurations, and a lot of careful handling. When the minimum turbulence in the ZooKeeper operation can really break it down. Also, many issues that people have seen with ZooKeeper are really around that running in cloud and containerized environment, as in the ZooKeeper was created in an era where everything was bare metal. And yes, you can translate bare metal into containers and cloud. There are subtle differences though in the way the networking works and so on, and all of these have effects, and people have been experiencing these kind of issues. For example, like with the sidecar TCP proxies like Istio. Yes, you can enable Istio in your Kubernetes cluster, and it's almost like the same, but when you run Istio and ZooKeeper on top of Istio, there were like things like bugs, like it's not a direct connection anymore. Now you have a TCP proxy in between. So ZooKeeper redirection will still work, but it might degrade worse than it was doing in bare metal. For example, you could take minutes to have a leader when running with the Istio in between. So there are a couple of reasons to detach a bit from ZooKeeper in the context of Pulsar. One is that for big cluster, we want to make sure that we don't have that upper limit on the number of metadata, because that number of metadata essentially limits us in the number of topics that we can store. So we would like to really have a horizontally scalable metadata store so that we can keep adding nodes and add capacity in terms of how much metadata throughput we can put and how much large cluster size we can have there. On the other side, for small clusters, really, it's a burden to run ZooKeeper and to operate it. So if you could have less components or easier components with easier operation for small cluster, that would also be a win. So this is kind of like two different angles for different reasons. So we started a couple years ago with this PIP 45, which was a plan with multiple steps. And really the first part was to replace all direct usage of ZooKeeper and instead I could route everything through a single dedicated API. And the idea is that we can, if we can do that, then we can have multiple implementations. So we can use ZooKeeper, we can use etcd, RocksDB, and memory, local memory. So we did start with this a couple years ago, and again, it was all over the place, and we kind of like tried to rationalize all the access metadata. And this was actually completed into .10 release. And once we started looking at it, there were like, the first step was to really try to understand how to use metadata, what kind of use cases for metadata do we have, what kind of access patterns. And we really like boiled down to kind of like two different patterns. One is really like simple, like key value access plus notifications. And notification is really important for having a cache so that we can cache that metadata in the brokers. For example, like you have the policies for your namespace, you change the configuration, each broker will have that configuration cached. So for example, like if you have your backlog quota for your namespace set to say 10 gigabytes, you change that, all the caches get invalidated, the brokers will pick up that change and they will apply the new quota. That will happen immediately. The second pattern is complex coordination. So complex coordination is like leader election, resource locks, and so on. So for key value access, really, we have this metadata store API, which essentially is this key value store access, where you have like this put, get, and delete, and it really deals with byte arrays. And user can register for notifications. On top of the metadata store, there is also a metadata cache API, which essentially it is an object cache on top of metadata store. So it's kind of like transparent cache. You can do writes and reads, and the reads will be cached as objects, so that we only deserialize it once, and then it gets cached as an as an object. Typically, it would be a JSON, or can be also protobuf, and so on. And the companion here is a coordination service, which is for a cluster coordination. The coordination service has three main APIs. One is the resource lock, which represents a distributed lock over a shared resource, and then the leader election, so that you can have different kind of leader elections, and then distributed counter to generate unique IDs. So all these are packaged and API as APIs that, and all the interaction within Pulsar are using these primitives, the key values and the coordination service. So there were like several wins that we got already by enabling metadata store APIs in Pulsar that are available into the .10, even by using ZooKeeper with them. And the first one is that since we have this consolidation of all the accesses through one single API, we are now able to have the broker to revalidate the session. So there's a concept of session in the coordination service, and all the aspects that are in the coordination service are able to get revalidated. So if you have a resource lock over some resource and we lose ZooKeeper session, we are able to get the broker to be up and continue to do the data path without getting restarted like it was before. So now the broker can keep going, we keep the data path intact, and once we reconnect to ZooKeeper, can be, say, after a ZooKeeper outage of a few minutes or 1 hour, the resource lock implementation will be able to revalidate the lock. So it will check what is in ZooKeeper, it will revalidate that, am I still the owner or not? And if it's still the owner, then perfect, fine. We can just go on without any interruption. We had a ZooKeeper outage, but we didn't have any Pulsar outage at this point. And similar with the etcd, that would be etcd release. So that is very important because this is a major cluster stability improvement. Before we had to basically kill the brokers because we couldn't guarantee that we could resync them. So the state can be in weird state, and there are so multiple combinations of possibilities of a Z node that we think it is there, and now it is not there anymore. But by having a single implementation, we can have all these conditions checked and revalidated so that we can see what we think we should be there, check ZooKeeper what it has, and then make a decision whether are we still the owner of this resource, of this topic, or we should give it up. And same for leader election. Am I still the leader for this kind of resource, or am I not anymore? The second aspect that it was also like a very good win is that by having everything routed into a single place, we don't use ZooKeeper API directly anymore, but we have our own layer. And in this layer, we could add, not just for ZooKeeper, but for every implementation, we could add transparent batching. So that means that if you have, like, say, trying to load a bunch of topics in a broker, we generate a lot of writes into ZooKeeper. And all these variable operations are queued internally, and we send up only a single batch for them at a given interval time. So that gives basically a huge improvement in the write throughput. So this goes from, in ZooKeeper goes from, say 18K to 92K just by enabling that. And read is like 10x improvement, even more than 10x, from 38K reads per second to 571K per second. So it's really a massive improvement that we get by all these exercise in having everything going through a single API. So now the question is, what is next after this? And the idea here is that we have this pluggable API. We do have two implementations mainly, which is ZooKeeper and etcd. And this goes with 210. And you can also mix and match and say use one for the local ZooKeeper and one for the configuration store. It is possible to add custom implementation. We have RocksDB that we use for standalone. We have memory, but it is actually it's not triggered, but it is easy to add more implementation. And we think of adding more and more implementation for, say, configuration store. For cloud environment, for example, that's one idea, instead of using ZooKeeper there. I encourage people to try out with etcd if you're already an etcd user and report back any issue to us. The other thing is that the point of this exercise was, one, to isolate all metadata access, but now is what would be the perfect state for metadata service? So eventually, like with ZooKeeper, because that was the best choice available when we started, but really, like what will serve better Pulsar would be something that with these properties, right? So we really want to have transparent horizontal scalability. So ideally, we want a system that is able to, we can add more nodes, add increased number of pods, and have more capacity. We will want to have ease of operations. So we want to basically able to add or remove nodes and replace nodes without any special handling. ZooKeeper is a bit picky about it, right? So you cannot add more nodes. You have to bootstrap them, and so it is not as easy. Another thing is that ZooKeeper, essentially, it is a single linearizable database. Essentially, like the entire dataset has a single story. So each time you do a write, there is a ZXID that gets incremented. So even if you write on different Z nodes, everything gets linearized into one single history. For us, we don't care about it. So we don't rely on this, and we don't need it. So we prefer to have some kind of like a sharded store, because we don't rely on having multi-node transactions. We only care about having conditional writes on a single Z node. The other part is the size of the data set. So ideally, we would like to get to a place in which we have data sets of like 100 gigabytes. And that is something that is normal, and that is not something that has to be handled with particular care. And in terms of read-write rates, ideally want to get to a place in which we have like 1 million operations per second. And typically, we don't do sustained rate about this, but it is very important to be able to absorb a large spikes of writes and reads, because when a broker changes ownership of a large number of topics, it will generate a lot of writes and reads. And we need to be able to absorb that spike very quickly with low latency and in the shortest amount of time. And with some latency targets that are not super exaggerated, but like reads around 5 milliseconds, 99 percentile, and writes like 20 milliseconds. So these are kind of like the perfect requirement that we will need. So we can give up linearizability of a global history, but we want to have this scalability, ease of operations, and larger data set. So we started like going back to the design table and the whiteboard and come up with a few ideas and a few guidelines. The first one is that we don't want to implement these directly in Pulsar brokers, like someone else has chosen the path. And the reason is that I don't think it is useful to like replace ZooKeeper with something that looks like ZooKeeper and behave like ZooKeeper, just put it in a different place, because you're kind of like getting the same architectural problems in a different place. And it doesn't reduce the complexity, it just moves the complexity from one external place, which is very well tested, into another place with a new implementation. So I really don't think it's the best way. Again, there are different opinions here. And the other part is that I don't think at this point in time it is useful to rewrite Paxos again. There are multiple Paxos implementations or Raft. So I don't want to get into that business because it takes probably 5 to 8 years to get a stable version out that is really battle tested. So I don't think that is the best route there. So I want to avoid that. The other part is that since we are designing in 2022, it is not, I think ZooKeeper was designed in 2008 or so. The first paper, I think it was 2007 even. So it was a completely different era. Now we have different primitives, different environments. We have cloud native environment, we have containers. So we can take very different decisions at this point instead of like going back and designing for bare metal. That's, yes, there is bare metal, but we can design especially for a different kind of environment and take advantage of this. If this simplifies the implementation and allows us to get something that works in a much easier and shortest amount of time. And finally, the other is that we really want to make sure that the system is designed from ground up for auto-tuning, as in you want to make sure that we have the least amount of operator intervention required to operate this kind of service, and running from a tiny cluster to a huge cluster without a lot of any intervention there. So let's say that we started with this bouncing these ideas, and the ultimate goal for this is really that we want to make sure that we can achieve a 10x increase in the number of topics that you can have in a cluster. And so right now you can run Pulsar with millions of topics. It requires a sizable enough cluster. So people from Yahoo can relate to that. They've been running millions of topics, but it was not like a 3-node cluster. It was a sizable cluster. But eventually we want to get to a point in which we can run these and without requiring a lot of like sweating over ZooKeeper and stuff, instead of just growing naturally and also having a small Pulsar cluster supporting many millions of topics. And the handling of the metadata, it is the bigger obstacle, right? So if we can solve this problem, we are halfway through. Although it is not the only problem, there are also other problems that we are working on in the Pulsar brokers to achieve this. And things like around the metrics is a major area of improvements to support many topics because on how efficiently metrics are collected and stored and exposed to the external systems. But things also like topic lookups, or like the overhead of a single topics, or having like global memory limits in the broker to make sure that even if you have a million topics in a broker, it doesn't exceed the memory limits. So I thank you for listening, and I know I didn't give lots of details, but this is where we're heading, and I hope that clarifies some of the things, and we'll be able to share more about this in a few months.